Okay, so we're going to... Oh, wow. Okay, we're going to talk about Boyles Law, Charles Law, a third one that's like kind of a lesser-known one called Gay-Lussac's Law, and then we're going to combine them all together into something called the Combined Gas Law. Really clever, okay? So, the third one is called Gay-Lussac's. I'll tell you that when we come up one by one. You don't have to write that part down. Okay, so we're going to start with Boyles Law first. Boyles Law. And Boyles Law relates pressure and volume of a gas. The pressure and the volume of a gas. Okay, and they have what we would consider an inverse relationship, which means when one goes up, the other goes down. Okay, so when we are looking at Boyles Law, we're looking at just the properties of pressure and volume. So when we talk about a gas, when we're observing Boyles Law, we have to understand that it's going to be constant temperature. Okay, so the temperature cannot affect the change there, and the mass or the amount of substance can't be changed either. Okay, so when we talk about Boyles Law, we're talking about pressure and volume. And so here's our equation for Boyles Law. P1V1 equals P2V2. What do you think the 1 and the 2 mean? Are they two separate substances?
The pressure before the change.
Perfect. Pressure before the change and after. So left side of the equation always means before, right side of the equation always means after. Okay, you could put an initial and a final in there. You could put before and after, whatever you want. But left side of the equation is always before, right side of the equation is always after. Okay, let's review a little bit. What do we like our units to be for pressure? Atmospheres, good, atmospheres. And there's lots of other versions of pressure, like torr, like PSI, like millimeters of mercury, and yep, kilopascals. Good. Those are our other big ones. Okay. Volume, we haven't talked about the unit yet for volume. Volume needs to be measured in liters. Okay, so I'll walk through what each of these variables mean. You don't have to write these down. You know that 1 means before, 2 means after. But P is pressure, has to be in atmospheres, or we would like it to be in atmospheres. V has to be in liters. Okay. I make some stipulations for the units because when we move on to our last gas law that we'll really talk about, the units are very specific. For these equations where we're just dealing with a before and an after, there's no constant value that we have to put in. Our units can fluctuate a little bit as long as they're consistent on both sides. So pressure could be in kilopascals as long as the final pressure is in kilopascals. Temperature could be in, volume could be in milliliters as long as the other side is in milliliters. So for these equations, we have a little flexibility in terms of units. When we deal with our last gas law, which is called the ideal gas law, we have a constant that has to go in there, and it has to have specific units. Okay? So the reason I want you to start working atmospheres and liters is because that's what our final gas law will need. So you need to be able to convert and use those units well. Okay? But understand, up until that point, we do have a little flexibility in terms of our units as long as we're consistent. Okay? Questions here? All right. Let's try one here. 1 liter of gas at STP is compressed. What's that mean? Yeah, it gets closer together. Not expanding. Okay, the opposite of expanding. Compress. You guys, can you hopefully that word is not too foreign for you. Compress just means get smaller. Okay? So it's compressed to 473 mils. What is the final pressure? Okay, so let's write out what we like here, or what we have. I'd like to list all of my variables here, like in the margins of my sheet. Okay, so you'll see me always make a list of what I have. When I deal with more than one variable, I like to make sure I know what I have. Okay, so 1 liter, is that my initial volume or my final volume? That's my initial volume. So V1 equals 1. At STP, this means this is my initial. Oops. And compressed 2, this is my final. Okay? When we read these gas law problems, you have to be able to use context clues to pick out what's the before and what's the after. Okay? So, at STP, what's that mean my initial pressure is? What are our conditions for STP? Remember, we gave those to you last class. Yeah, 1 atmosphere. Okay? Do we care about what the temperature is? No, not for right now, right? We know we're doing Boyles Law. We know that the temperature has to stay constant. There's nothing here that's changing in terms of the temperature, so we don't even really need to write that down. Uh-huh. For Boyles Law, we won't use temperature. Okay? For other laws, we will have to. Okay? Because when something stays constant, if we would plug it into our equation, we would multiply by it and then divide by it. So there's no point in putting it in. Okay? It says at STP, that's a condition, right? STP is standard temperature and pressure. So if something is at STP, we wrote it down that it's 0 degrees. Okay, so our final volume, can we keep that in milliliters? No, we can't because our initial was in liters. Okay, if our initial would have been in milliliters, we could have kept it. We want to make them consistent. So our easiest way is just going to be to convert that to liters. So how do we go from milliliters to liters? Do what to 1,000? Divide by 1,000. So it would become 0.473 liters. Okay, then when I set that up, I would take 1 times 1 equals P2 times 0.473. Okay, if I want to get P2 by itself, right, what's the final pressure? So over here I would go ahead and write P2 and then I just write a question mark. That way I know what I'm solving for. You don't have to do that, but it gives me an idea, so I make sure I solve for the correct equation. I'm sorry, the correct variable. So when I plug that in, what am I going to do to that 0.473? Divide it over. So I take 1 divided by 0.473, which gives me P2 of 2.11 atmospheres. Right, I would divide this over 0.473, divide by 0.473. I got 2.11. Agreed or not so much? Go ahead and grab your calculator if you don't have that yet. Let's think about this now in terms of kinetic molecular theory that we learned last class. Okay, our temperature is constant, so we have the same amount of kinetic energy for the whole time. We start with a liter of gas and we shrink it down. What has to happen to those molecules now as we shrink the amount of space they have available to them? The pressure has to increase. If temperature is going to stay the same, that means kinetic energy is going to stay the same, those molecules are going to be hitting the walls of that container a lot more often, right? If the walls move in toward them, they're going to be hitting the walls of that container a lot more often, and that's essentially what creates pressure. Okay, the temperature itself is staying the same, so we're not moving necessarily any faster. It's just that we're going to hit the walls of the container a lot more. Yeah, we have less space, so we're going to have basically more crowding with those gas particles. Okay, does that kind of make sense? Hopefully we can see kind of the relationship between those. Okay, go ahead and try this one on your own. With these gas law problems, you don't really need to write down the whole problem. You're more than welcome to, but I would go ahead and definitely make sure that you're writing down what you have. So in terms of V1, P1, V2, and P2. As we just look at this problem, should be easy for us to think about or to guess an answer here, or at least predict. Do we expect our pressure to go up or to go down? What happens to our volume? Our volume is decreasing, so our pressure should increase. Okay, that's the inverse relationship we were talking about. So we start with 5.6. We have a pressure of 1.5 atmospheres. We compress it until we have 4.8, and we solve for P2. Good, 1.75, and our units are atmospheres. Good. Okay. Units are atmospheres because that's what our initial pressure unit was. That means it's got to come out that way in our final pressure. Okay. Together. And this one we got to read pretty carefully. Okay, a balloon is filled with 835 mils of air at a pressure of 782 millimeters of mercury, and I add 424 milliliters of air to the balloon. What will the final pressure be? The initial we have What is the initial volume here? So V1 is 835 milliliters. And let's go ahead and put that into liters. So 0.835 liters. Our pressure is in millimeters of mercury. We really don't want to work in millimeters of mercury. Okay, so how could I convert that from millimeters of mercury to atmospheres? Yeah, do a T-chart. What's the conversion? 760, good. And we're going to divide by 760. Atmosphere should have a smaller number relative to the other pressure units. Okay, so that gives us about 1.03 atmospheres. I took 782 and I just kind of did a T-chart in my head and divided by 760. Okay. So then for our final volume, is my final volume just 424? No, what's happening if I put air into a balloon? What happens to the volume of the balloon? It's going up, right? So that means I would take 0.835 plus 0.424 to get my final volume. Okay, and these problems you're not always going to solve for P2. I don't know why all my examples have a solve for second pressure. Okay, that's not always the case, but algebraically you're going to still solve them the same way. Okay, so don't let that throw you off if you have to solve for something else besides final pressure. Okay, so when we plug it in, we would say P1, which is 1.03 times V1 equals P2 times V2, 1.295. Okay, so I'd multiply everything on the left. We get 0.86 equals 1.295 P2. I would divide by 1.295. 259, you are right. Thank you. Okay, so 0.86 divided by 1.259. 0.683? You can keep it at 0.68, that's fine. Okay, so again, you're not always going to be solving for final pressure. I'm not sure why I had all those examples solving for P2, but you're going to solve it the same way. Charles' law is the relationship now between volume and temperature. Okay, so if it's between volume and temperature, what has to be constant? What's not changing? Pressure, good. Okay, pressure is not going to change.
So Boyles law is between what?
Boyles law is between pressure and volume. And Charles' now is volume and temperature. Okay, when we see a direct relationship, what happens as my volume increases? My temperature also increases. So this is a direct relationship. So when one goes up, the other goes up. When we talked about pressure and volume and their relationship, they were inversely related. So if one goes up, the other goes down. Okay, so that graph would maybe look something like this. Volume versus pressure. If one goes up, the other goes down. Okay, it would look something like that, I think. Okay, on an inverse. And probably not quite so straight, more like that. Okay. But that's essentially what that would look like, I think. All right, so here's our equation for Charles' law. V1 over T1 equals V2 over T2. The 1 and the 2, again, just stand for initial and final. All right, so our initial volume here, V1 is 67. T1, do we want them in Celsius or Kelvin? Kelvin. We want them Kelvin. Okay, and this is why. What if one of our temperatures was 0 degrees Celsius? Okay, then that would not allow us to do the math to solve for anything else because we'd have a 0 and a fraction. So we have to make sure that we're keeping that in Kelvin. So to go from Celsius to Kelvin, we add 273. Okay, we're in liters and Kelvin just like we want to be. So V1 over T1, so 67 over 301 equals V2 over 320. This type of ratio or kind of proportion here allows us to do what to solve it?
Cross multiply.
Yep, cross multiply and divide. Okay, so it makes for pretty easy math. What do we expect the volume to do? Go up or go down? Up. Goes up. Okay, our temperature increased. Our pressure had to stay the same, which means as our molecules started moving faster and faster and gaining more energy, they hit the walls of the container. But since our pressure needed to remain constant, that allowed the walls of the container to literally expand. Okay? That's what we see there. So our second volume, or our final volume here, Laura, what'd you have?
71.23.
Good. 71.23 liters. Perfect. Okay. Questions there? Okay. Go ahead and try this one on your own. Yeah.
Would you want us to convert it back to Celsius?
No, most of the time I'll take either one. Yeah. All right, good. Last one here for Charles' Law. How hot will a 2,300 milliliter balloon have to get to expand to a 4,000 milliliter balloon? Assume the initial temperature was 25 degrees Celsius.
Do you want us to keep it in liters now, or can we keep it in
You can keep it in milliliters if you want. I mean, even in these ones, you can keep it in Celsius if you want. But I'm just telling you, for future-proofing yourself, it's good practice to start converting milliliters and Kelvin. Up to you. Okay, in Kelvin, what did we have? 500 and... Okay, very good. So between Charles, Boyles, and Gay-Lussac's, this is kind of the least common, not really sure why, but it is. But this is when we look at the relationship between pressure and temperature. So since they're directly related, it looks almost like our Charles' Law equation. Okay, so it's P1 over T1 equals P2 over T2. So we're just going to do one here with Gay-Lussac's law. Determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 degrees to 30 degrees. And when we cross multiply and divide, we end up getting about 1.03 atmospheres. Okay, so our pressure change is not very significant, right? Our temperature change is not very significant. So as we see that direct relationship, one goes up, the other goes up, we see it going with kind of the amount also. Okay, so our pressure didn't go up very much because our temperature didn't go up very much. Okay. The last thing that we're going to look at today is the combination of those three gas laws into one equation, which is called the combined gas law. Okay? So if you had to predict, what would it look like? Can anyone predict what the equation might look like?
V1 over T1.
Yeah. Okay. P1 V1 over T1 equals P2 V2 over T2. The reason that we're able to predict this is we can break them down into the three. So this one is Boyles. This one is Charles. And this one is Gay-Lussac's. Okay, so we can see all three of those gas laws come together in one. Okay. Were we not seeing that? Now we are. Okay. All three of those are put together in one. So let's talk about how can you remember which one is which? How do you remember what law is named what? And I learned this kind of trick when I was student teaching, and I think it's pretty helpful. So when we're trying to think about Boyles Law, okay, which one is Boyles Law?
Volume pressure.
Volume and pressure, the first one. So this is Boyles Law right here. So what is left off? What remains constant during Boyles Law? Temperature, okay? So when you boil something, right, when you boil water or boil something, what's the temperature of the water? Does the water go up or down?
Yeah.
No. When you boil something, you're at constant temperature.
When you boil it, the water gets hotter.
Well, when it's boiling, the water remains constant, okay? So when you boil something, you've got constant temperature, okay? So that's the way you can think about that. Boil means constant temperature, okay? Boil, boil. Okay. The next one, I don't think as quite as a handy way to remember it, but the next one is for Charles' law, which is V1 over T1 equals V2 over T2. So what's constant here? Pressure, okay? And I don't really know much about Charlie Brown, but this is how they told our class to remember it, is that Charlie Brown is always under pressure, okay? So he's under constant pressure. So Charlie Brown is under pressure. Charles' law is constant pressure. Okay, so boil is constant temperature, so it means you leave it out. Charles is constant pressure, which means you leave it out. Okay? Use it if you want. I don't really care. Just if that helps. Okay? All right. This is a lot of words for not very much information, so you don't need to write down the whole problem.
How do you remember this?
Sift through it. Okay, so I put in red the initial, and I put in purple the final. Do we care the fact that it rose 3 kilometers into the air? No, we don't care. Okay, so you got to think about weeding out the information that you don't need. Okay. So V1 equals 1.8. P1 equals 1 atmosphere, and T1 equals 293 Kelvin. So if it's at negative 10 degrees Celsius, we're just going to take negative 10 plus 273. Okay, so we're just getting 263 there. Okay, we cross multiply and divide here. Or really more simply, I like to do this whole term first, right? I would multiply on the top, then divide by that bottom, because it doesn't have a variable on that side. You can still cross multiply and divide if you want, that's fine. Algebraically, you can do it however you want to get there, but realistically, I would do the whole left side first. 1.8 divided by 293, that would leave us with 0.006 equals 0.667 V2 over 263. And from there, I would multiply here, and then I would divide by the 0.667. Okay, you don't have to do it that way. Whatever works best for you is fine. But final volume, I got to be about 2.42 liters. Try this one on your own. Get everything converted to atmospheres and Kelvin. And liters.
Yes. Yes.
So this one leads to a pretty easy cross multiply and divide, okay, when we're solving for temperature. But that's up to you.